Derivation of centripetal accelerations. So centripetal acceleration is equal to the negative of the angular velocity, square of the angular velocity times the radius here. R is the radius. So this is the formula for centripetal acceleration in uniform circular motion. Here's the step-by-step derivations. Position vector. So consider a particle moving in a circle of radius r with constant angular velocity, this is omega. So in the 2D plane using x and y coordinates, the position vector r as a function of t here at any time t is given by r as a function of t. So this is the radius. R times this is the absolute value of r cosine of the product of the angular velocity times the times. So we have the unit vector along the x-axis times plus r here times the sine of the angular velocity times the time times the unit vector along the y-axis. Now g here is the unit vector along the y-axis, where I and g are the unit vectors along the x and y-axis. So we have the velocity vector. Velocity v is the time. The velocity v here is the vector. It is the time derivative of the position vector v equal to dr over dt. So using the chain rule here, so v as a function of time here, this is the velocity. The derivative of r here. So this is the given r. So the derivative of this is given by negative r angular velocity times the sine of the angular velocity times the time times the unit vector along the x-axis plus r times the angular velocity times the cosine of the angular velocity times the times the unit vector along the y-axis. Acceleration vector. So acceleration a is the time derivative of the velocity vector. So a is equal to dv over dt. Derivative of time, derivative of velocity with respect to time is equal to acceleration. So we take another derivative here. So this is the derivative of the velocity. So this is the derivative of the velocity. Now factoring out the negative of the velocity, the angular velocity square here. So we have the negative square of the angular velocity times r cosine. Now this expression, this one is equal to r. So finally we have that's the reason why the vector acceleration is equal to negative of the square of the uh, angular velocity times r here. So r, this one is equal to r. Now we have the physical intuition here. The acceleration is proportional to the square of the angular velocity. How fast it spins. Spin twice as fast. And the centripetal force needed increases by a factor of 4. So r here is the acceleration vector points in the same direction as the radius vector towards the center of the circle. The minus sign here, the position vector r points away from the center of the circle outward. The negative sign indicates that the acceleration vector points in the opposite directions of position, meaning the acceleration here points toward the center of the circle. This is why it is called the centripetal center-seeking accelerations. The animated vector plot here, the visualizing the physics. So this code creates an animation showing a particle moving in a circle with both the position vector and the acceleration vector A plotted as arrows. So we have here, so we have the vector R here. We have the direction of the direction of R here is away, but the direction of the angular acceleration is towards the center. So like this one, so we have the R, and the direction of the angular acceleration is towards the center here. So interpretation of the plot, when you run this code, the red arrow are here points from the center outwards towards the particle on the circle. So the blue arrow here points from the center inwards, opposite the direction of R. So the length here, the blue arrow is exactly the square of the angular velocity times longer than the red arrow in the static example. In the static example, the omega here is equal to 2. The blue arrow is equal to 4 times longer. So inversion, you will clearly see that the acceleration vector is mirrored, scale the reflection of the position vector red across the origin, which perfectly visualizes the negative of the angular velocity part of the formula.